quiz tomorrow. Calculus Carol's on Friday. Should have the quiz graded, hopefully. And so we can go over that real quick on Friday, and then leave some time for the Calculus Carol extra credit thing. So 4.1, we talked about the things you need to know, those 4 things you need to know from there. And then 4.2, all these limit problems. So very much be about, the limit problems be very much like what was on the homework here today, last couple of, just these limit problems, find the limit. And so let's focus on that first. I've got a little worksheet here with some limit problem examples, and then a Newton's Law of Cooling problem too for you to practice. But again, with Newton's Law of Cooling, it's essentially this formula right here. You just have to know that formula. You have to know the parts of that formula. Room temperature, A and K, you just find by plugging in those initial conditions. You solve on your calculator for temperature Y and for time T. And it's pretty straightforward there. But you have to go through it. So I've got one you can practice again for that. Okay, but a big part of the points are probably limits. That's probably half or close to half of the points. So important to do that. The matching the slope fields, drawing the slope fields, where you draw your little slope segments on there. And then sketching your solution curve inside of a slope field, right, where you just given an initial condition and you sketch and follow the slope segments. So
this is a pretty easy test.
Well, I would think matching slope fields should be, right? The problem with matching is you get off on a couple, right? And then that's, they kind of come in pairs a little bit. And that's kind of how I grade it. If you get, I think if there's 8 of them, 8 matching, I think if you, that might be worth 4 points, right? So because if you miss one, you're going to miss another one, right? For sure. And so I think it's like a point for each pair that you might miss. And then slope fields, drawing that be worth a certain amount of points. Sketching a solution curve, they mostly would be pretty easy. Newton's Law of Cooling should be pretty straightforward, there. And then the limit problems, some of those can get trickier than others, and so, I always hesitate to say it's going to be easy, so that's kind of relative. But some of the limit problems can be, so let's talk about those. Let's go into those. So here's kind of that summary that we had up here yesterday of what to do. So it's very similar. You have 2 different types of limit problems. Either x is approaching a number or x is approaching positive or negative infinity, right? Those are 2 really different kind of things. X approaches a number, you're talking about the cars meeting kind of thing. And so that's either at a number or maybe there's a hole in the graph, right? So if you get 0 over 0, remember 0 over 0 is typically like a hole in the graph. So you don't get 0 over 0 when you're doing x approaches infinity, right? You get 0 over 0 when you're doing one of these. You get infinity over infinity or 0 over infinity when you're doing an x approaches infinity. But so if you're doing x approaches 3, you might get 0 over 0, which typically means a hole in the graph, but the cars might still meet. So you keep going. So you do one of these 3 things here, possibly. Now, we haven't done much with these algebra things. Probably not going to have to do much. Doesn't mean you shouldn't. Maybe there will be one where you have to get a common denominator or a conjugate method. I think on my worksheet, I might have one on there where you could do it that way. But remember, when you get 0 over 0, what is your other option now? L'Hopital's rule, right? When you get 0 over 0, we've now added this option of L'Hopital's rule. See, so you don't have to do the conjugate or a least common denominator. You could do L'Hopital's rule if you get 0 over 0. So even if there is one on there like that, it's up to you. You want to use, some of those algebraic techniques we talked about, you still can. But you could do L'Hopital's rule also. Okay? And so you still might get an answer. When you get one of these indeterminate, this number 2 in here, these are all indeterminate forms. Okay, and indeterminate means, hey, keep going. There's some way to get it, possibly. And so you do one of these or this new thing, L'Hopital's rule, or we can just ask the question like we did 2 days ago before we knew L'Hopital's rule. We just, can we look and say that the top's getting bigger, a lot bigger than the bottom or something like that. So maybe we can come up with it that way as well. Okay, so there's just kind of a variety. So most of your work is done in this section here, because that's what happens a lot of the time. But then you're also going to get into some here, where you get a number over 0. Now that, again, typically happens when you have x approaches a number. That's when you usually get this kind of thing. Now, understand, we had this yesterday. Go back to something Jordan asked, where he talked about 0 and infinity being reciprocals in a sense, and that's true. And it's actually any number, any constant. Yesterday I had 1 over 0 and 1 over infinity. It could be any constant over 0 or any constant over infinity. Whenever you get a constant over 0, constant other than 0, by the way, right? 0 over 0 is its own category. If you get a constant over 0, we know that's going to be infinity. So we've added that in here the last couple days. In the past, in chapter 2, if you got a number over 0, we would just say does not exist. Okay? But now we understand, hopefully after the next couple days, we know a number over 0 is infinity. Right? Jordan said it yesterday. We wrote it up here on the board. We know that's what's happening. Now, the only reason we have to do a little more here, the reason we have to tell why, the reason we have to check on the right and the left when we get a number over 0 is we don't know if it's positive or negative infinity. That's why I put those question marks in. That's the reason you check the left and the right. So when you get a number over 0, yes, that means infinity. It means vertical asymptote. We just don't know if it's going to positive or negative, and I want you to tell me which it's doing. So that's why you keep going as far as adding in this extra information. You check the left and the right to tell me if it's going to positive or negative infinity. That's the only difference. And if we get a number over infinity, it doesn't matter here if it's plus or minus infinity. It doesn't matter. You get a number over infinity, that's going to be 0. That's going to go towards 0. Okay? All right. So again, we've added that into here. When you get a number over 0, that means vertical asymptote. It means infinity because over there, and we're just checking the left and the right side to see which it is. Okay? So again, it's kind of a lot of stuff to keep straight, but yet if you're kind of seeing the big picture of it, of what's happening, then maybe it isn't that hard. Okay, so which ones on the homework do you want to look at? Katie, what was that, 58? Let's do this one. I know you may not have done this one. Now remember, I suggested to do more, and maybe if you didn't do all of them, which is fine, you can do some more tonight, right? I've got some on this worksheet, but doing some more in that group of 56 through 80, right, would be a good idea. And so Katie had asked me about 58, and I thought something interesting happened on that one that relates to what we were just talking about. So let's investigate that one. So what did it say? Limit as x approaches. What was it, Katie? I don't remember. Was that just 0, or was that 0 from the right? That was 0 from the right. And go ahead. Okay, it's that problem right there. Okay? Now, oftentimes when you get 0 from the right or something from the right or the left, it has to do with domain, kind of like that natural log we had yesterday, right? So there's nothing really different or special you have to do here, but why would they want to do 0 from the right on this one?
Because you can't have it.
Right, you can't do square root of negative. So if we go 0 on the left, they'd be negative x's, and then you'd have square root to be undefined there. So this function is not going to have any negative x's. Its domain is going to be just positive and greater than or equal to 0 just because of that square root of x, right? So that's why they put the plus there. So it doesn't really change much as far as what you plug in. And one of the things Katie and I talked about is we were talking about plugging in like a 0.0001 and stuff like that. And you do not have to do that here. What's the only time so far that we've been plugging in like a 3.001 or a 2.999?
Finding out if the infinity is positive or negative.
When we're doing this thing down here, right? That's the only time we're doing that, when we get a number over 0, and then we want to check the left and the right of that number. So if x approaches 3, we get something over 0, that's when we're doing it on a vertical asymptote, right? Because this is all no calculator, right? So you're not going to be plugging in a bunch of stuff. Now, I mean, I say that, yeah, you're going to be plugging in, like here, you're plugging a 0, but you're not going to be plugging in a lot of 1.001, that kind of thing. Only in that vertical asymptote situation do you have to do that. So we plug in our 0, what do you get on top? Sine of 0? 0. 0 plus 0? 0. Okay? Going to happen quite a bit, right? 0, 0, infinity, infinity, those are going to be probably happen quite a few times, right, in these problems. So what do you get? What do you do? I would say L'Hopital's rule would be a good thing to do, right? This one isn't really a how fast is this one going to 0, this one's getting small, the bottom's getting small. This isn't really one of those things we would be able to do. That kind of thing on it. It's not a factor problem, it's not any of those other things. L'Hopital's rule, right? 0, 0, that's what I would do. So, here we go. Top would be cosine of x.
1 plus 1/2 x to the negative.
Now, I think this is such a common derivative to do that it might be worth starting to memorize this one, because this is not a lot of fun to plug numbers into or solve or anything. So what would this negative would go to the bottom, and it would be this right here. Is that correct?
Yeah.
I think that's one that might be worth some memorization on, that the square root of x, I mean, is the derivative is that, because it seems like that's the form we usually, it's a lot easier to work with. Okay, so anyway, that's what the derivative of square root of x is. Okay, so now what do we do after we've done that? Now we plug in our 0, right? We plug in our 0. Now what do you get right here? Let's start up here. What's cosine of 0? 1. And then what do you get down here? You get 1 over 0 here, right? So, but then, yeah, so all of a sudden your thought is that's undefined, right? And then I could see you'd get confused. Oh, gee, I don't know what to do, right? Because it's not 0 over 0. It's not anything we do, L'Hopital's or anything like that. It's just 1 over 0. Well, that's where I think this over here comes in real handy, right? 1 over 0 is what? Infinity. Right? I think you'd be better served in this problem to think of that. 1 over 0. Oh, 1 over 0. That's infinity, right? Now, it's not, the difference is this isn't, we're getting 1 over 0, but we're not talking about this, right? We didn't get 1 over 0 at the beginning. That's when you go to this thing, right? Right now, it's in our best interest to just think that is infinity right here, right? As x goes to 0, this fraction is going to get bigger and bigger and bigger. Plus 1, the 1 doesn't matter. So what's on the bottom of this thing? Infinity. So basically what I have is 1 over infinity, which is 0. Right? What you have is as x is going to 0, as x goes to 0, this bottom is going to 0, which makes this fraction go to infinity, with plus 1 makes the bottom, this whole bottom is getting bigger and bigger and bigger, and the top is just 1. So 1 over infinity is 0, and that's how you would go through that. So you use L'Hopital's rule, but even then, when you plug in with L'Hopital's rule, you kind of have to think your way through it a little bit. Okay? All right, so as you're in the middle of these problems and you're plugging in, don't forget about these things here. But again, the number over 0, again, means infinity. We don't care about the plus or minus here. Now, if you want to think about it, x is approaching 0 from the right, right? So this is going to 0, but it's going to be positive. So this is getting to be a small positive. So 1 divided by a small positive would be a big positive. So if you want to think about it, you could. But it really doesn't matter if this is plus or minus infinity down here. It doesn't really matter. Okay, it's going to be 0, just like what we see up there. All right. So that was a good one. Another one.
76.
70. Okay, I've got 3 people raise their hand. He just shouts it out, which is fine. 76. Okay, so read it to me, Gabe.
the limit as x approaches 0 from the right. Sine x, natural log of sine x.
Sine x times?
Yeah, times natural log of sine x.
Okay. So you plug in a 0. You get sine of 0. Then you get, which is 0. Then you get ln of 0. Right, okay. So again, this is what I'm talking about when we can plug in numbers when we do limit problems. However, keep in mind that we really don't care. I mean, this goes back to the diner burning down, right? We really don't care what happens at 0 though, right? Do we? What we really are saying is that it gets close to 0, right? So now we kind of back up. We say, okay, wait, that's undefined. Well, we got to have something here. So now we're talking about 0 from the right. So think of the sine graph. Think of a car coming in the right side of the sine graph, and it's coming down towards the origin, right? At 0. But it's on which side, positive or negative? It's above the x-axis. So we're talking about this is 0, but what we really mean is it's going towards 0 from the positive. Right? So we're talking about really small positives. So now that's what we're putting into natural log. So now you got to picture the natural log graph. And we're plugging in really small positives into the natural log graph. Well, here's a natural log graph. So what is this actually equaling here? Negative infinity. That's what that is. So when we say undefined, you're right. ln of 0 is undefined. You can't plug in a 0. But we're not really plugging in a 0. What we're doing is we're plugging in 0, close to 0 from the right. So on the sine graph, close to 0 from the right is really small positives. Okay? And then we're plugging in really small positives into natural log. Well, those are going way down here. So this is really negative infinity. So you've got to be able to put that together. Not on every problem, but on some. Okay? And then you plug a 0 here, what do you get? 0. So again, that's one of our 0 times infinity situation. So what do we say to do in one of those? We need to get something flipped to the bottom, right? So which one? It probably doesn't matter. I would say sine maybe, right? Because that would just be less stuff. So let's do ln sine x, and then down here would be what? Sine to the -1. Now we could call that cosecant, but it's probably easier to do it this. To be honest with you. Now, it's not arc sine, remember, right? That's why I don't like that notation. This is literally -1 power, okay? So we move that to the bottom as that. Okay, so now it should be infinity over infinity, right? Because what have we done? We've taken the sine, which was 0, and we've done the reciprocal of that. What's the reciprocal of 0? Infinity, right? So automatically, when you have a 0 times infinity, you take one of them, flip it down. You either have 0 over 0 or infinity over infinity. It doesn't really matter that you write that down. You know you're going to have one of them. You can use L'Hopital's rule. That's the idea. So what's the derivative of the top? 1 over sine times the derivative of the inside, which is cosine. Right? Being proficient with the gateway test would be important here, wouldn't it? Okay, so that's the derivative of the top. What's the derivative of the bottom? -1. Leave the sine alone to the -2 times cosine. Derivative of the inside. Alright? So now what? Can you cancel the cosines?
Yes.
I think so, right? That doesn't really matter because eventually we're going to plug in a 0 here, right? We're going to plug in a 0. Cosine of 0 is 1 anyway, but whatever. Okay? Now, could you plug in a 0 right now? I suppose you could, but I would say there might be a little bit of simplifying we can do here that might be better. So this is 1 over sine, and this is 1 over sine squared. So what could you do with a 1 over sine squared down at the bottom? Yeah, I don't know. I always get nervous canceling when I have this. Here's what I would do, but I think you're right. This would be 1 over sine, and then this would be -1 over sine squared, right? Isn't that what this would be down here?
Yeah.
So can I invert and multiply here?
Yep.
Okay. So what I have is 1 over sine times negative sine squared. Isn't that what I'd have here? Right? Invert, multiply. And so wouldn't this cancel one of these? Right? And so what I end up with, now I can put a 0 in, and what do I get? Sine of 0. 0. Okay. So there you go. So, you know, the tricky part of that was the derivative part of it, probably, and some algebra simplifying. But I think this is really kind of important. Actually, as a matter of fact, I wanted to go back and do what I did for you yesterday because I didn't finish it very well. I totally forgot about this, which is something I usually try to remind people because it's common for you guys to forget about too. And then I actually modeled that because I forgot. When you do L'Hopital's rule, oftentimes it's kind of messy. Okay, because you have stuff on top, stuff on bottom. Simplifying that as much as you can before you go and then plug in is usually a good idea. Now, the one we had yesterday, was that the right answer, by the way? Did anybody check that? Oh, looks right. Okay, wouldn't be bad to check that one out. We had one yesterday that was ln x, I think it was. It was x approaches 0 from the right. Matter of fact, I should, you know, I don't think I still have it. And I think it was ln x on top and x to the 2/3. You guys remember that one? On the bottom. And we went back, and it was one we had in the homework before we knew L'Hopital's rule, and then we did it with L'Hopital's rule, but I don't think I did a very good job of finishing L'Hopital's rule on this one. This one, when you put a 0 into natural log from the right, that's negative infinity. And you put a 0 into here. Oh, wait a minute. It was approaching infinity. Thank you. So approaching infinity, so way out to the right, natural log is getting bigger, 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 so that's infinity. And then this is infinity as well. Okay, so it was infinity over infinity. So we did that. We did L'Hopital's rule. We got 1 over x. And then here we got 2/3 x to the negative 1/3. And this would be very much like the one we just did. Because now what we have is 1 over x. And then we have 2 over 3x to the 1/3. And I think this is the one, and I don't think I finished this one very well because here I think you should invert and multiply as well. And I don't think we did that yesterday. Okay, correct me if I'm wrong, but and maybe it was a different one, but this one we should invert and multiply as well. And this would be 3x to the 1/3 over 2. And then what can you do with these x's? Subtract, yeah, it's hard to count, but it's subtract the powers, right? Because what I have is 3x to the 1/3 over 2x, and so what I can do is subtract those powers, which would be what? It'd be 3/2 x to the negative 2/3, 1/3 take away 1, and now I can put that x on the bottom, and so this would be 2x to the 2/3, and now as x gets big, what's the bottom do? Gets big, so we end up with 3 over infinity, which is 0, right? 3 over infinity. Again, like we said over there, would be 0. So I'm not sure we finished that one. I think we talked about. I think we stopped here and we talked about getting big versus getting smaller, getting bigger faster. And I'm not sure that's probably the best way to do that. I think you should go ahead and try to simplify that when you have x's and stuff where you can invert, multiply, and subtract powers or add powers or whatever the case may be. So a lot like what we ended up with this one, the signs, where we can cancel and stuff. I think you're a lot better off trying to do that as much as you can. All right, another one. Nicole, what'd you have?
72.
72. Read that one.
The limit I get the equation I have is ln sin x over x minus pi times 1 squared.
Okay, so sine of pi halves is 1, right? ln of 1. Where does that cross right there? Okay? That's the 0.10 on the natural log graph. ln of 1, right? We need to know that. ln of 1 is 0. ln of e, those are two things we just need to know. ln of e is 1 and ln of 1 is 0. So we put a pi halves in for sine. Sine of pi halves is 1. ln 1 is 0. So we get 0. Pi halves minus pi halves is 0. So this is a 0 over 0. Okay? So I would say L'Hopital's rule. Again, there's not many options here. There's none of our algebra stuff that would work here. So derivative at the top be 1 over sine x times cosine x. All over the derivative of this, you bring a 2 down in front, you leave the x minus pi halves alone to the first times the derivative inside. Derivative of the inside is 1. Right? Now we can plug in our pi halves. What's cosine of pi halves? 0. What's sine of pi halves? 1. 1 over 1 times 0, that is 0. Put in pi halves. Pi halves minus pi halves is 0. Oh. So, what do we got? Do it again. Now, what would be a good way to write the top here? Cotangent. I think cotangent might be better than doing cosine over sine because then you have a quotient rule when you do the derivative at the top. So I think this would be better. And then we have 2. Might be good to write that as 2x minus pi at this point, right? Might be good to distribute that. Not necessary, but it might be good to distribute that. Okay? Since there's no power on that. All right, now, again, we're getting 0, 0. So now the derivative. What's the derivative of cotangent? Tangent. What's the derivative of tangent? Secant squared. So what's cotangent? Negative cosecant squared. Okay? Over, what's the derivative of the bottom? 2. Right? Now cosecant, the reciprocal of that is sine, right? So that could just move down as a sine on the bottom. The negative I'll just keep there. So this would be, and it's squared, that's fine too. Cosecant squared, reciprocal is sine squared, right? Any power of it, the reciprocal is still that. Okay? The reciprocal of 3 is 1/3. The reciprocal of 3 squared is 1 over 3 squared, right? So it's the same thing, so we can do that. And now we put in our pi halves. What's sine of pi halves? 1 squared is 1 times 2 is 2. So we get that. Okay? So L'Hopital's rule twice. Okay? Yes, Lynn.
16.
Number 60. What do you got?
It is, as the limit of x equals 0
Okay?
is tangent of 3x over ln 1 plus x.
Okay? So, put in a 0, tangent of 0. Remember, tangent is sine over cosine. So if you have trouble plugging into tangent, plug into sine, plug into cosine, do that. So sine of put in a 0, sine of 0 is 0, cosine of 0 is 1. So 0 over 1 is 0. Okay, so tangent of 0 is 0. Okay? And put a 0 in here, you get ln 1. What's ln 1? 0. So this is 0. Right? So that's the first thing, right? I can envision there could be some difficulty plugging into these things and seeing what you're getting. Okay, again, L'Hopital's rule. So, derivative at the top. Take out a 3. Over.
1 over 1 plus x.
Derivative of that is 1 over 1 plus x times the derivative inside, which is just 1. Okay? And now it might be good. I don't like plugging into secant. I'd rather plug into sines and cosines. So wouldn't that be this on the top? And this on the bottom? Right? 3 secant squared is the same as 3 over cosine squared. Right? So now let's plug in our 0. Cosine, 3 times 0 is 0. What's cosine of 0? 1 squared is 1, so the top is 3 over 1. Put in a 0 here. 1 over 1. There we go. Okay, so L'Hopital's rule is pretty slick here as far as it goes. Well, you gotta be able to do derivatives, right? Gotta be able to plug in and know these different values. Okay. What else? Any others? Okay. Yeah. What do you got? Okay, so and this graph is f right here,
Yeah.
correct? All right, so here's our limit down here at the bottom. So we first plug in a 4, so we would have f of 4. So we come over here, f of 4 is what? Is that 3.5?
Yeah.
And then this is x minus 4 squared. So f of 4 is 3.5, and 4 minus 4 is 0. So what do we got? Okay. Now we got to do right and left. So what do we got? So this would be just like plugging into a function right away from the beginning. Now, every one we've done so far, those other ones, it was 0 over 0, weren't they? They were all 0 over 0. And so we were doing L'Hopital's rule, right? But here, right from the get-go, and then there was that one, 58 we did, and after we did that, we, in the middle of the problem, ended up with like a 1 over 0. Well, then we just called that infinity and went about our business and kept going. But here, right from the get-go, we get something over 0. So we know that's infinity, but we just don't know if it's positive or negative, so we know the limit does not exist, so right away we can say does not exist. Okay, so we know that. But we need to say, because we know there's some vertical asymptote of this function, not on this function, this is f, we're talking about this function. This function right here has a vertical asymptote, that's what we know. So we need to check the left side of 4, and we need to check the right side of 4. Right? Now the difference here is we have a graph. I don't anticipate giving you one like this for a graph. We would have a function to plug into, but it's the same thing, right? We got a function to plug into. There it is. It's a graph we plug into. We look at the x's, see what the y's are. Okay, so what's to the left of 4? That'd be like 3.999, right? So what would we get if we go just to the left of 4? Well, we get about 3.5, right? So 3.49999, whatever. Not quite 3.5, right? What do we get on the bottom if we put in a 3.999? We get 3.999 minus 4 to be negative 0.001 squared positive 0.001. So it's going to be a positive small or something like that. What happens when you divide this positive divided by this small positive? Big positive, right? We knew we were going to infinity. We just didn't know if it was positive or negative infinity. That's what we're looking for. Okay, what about I put in 4.001? Well, put in 4.001 into f, you get, again, just a little bit below, right? 3.5, right? But that's, I don't really care about that. I don't care about that number. What I care about is the bottom. Put 4.01 in here, minus 4 is 0.01, square it. Also positive 0.001. So what do I get? I get infinity on both of them. See, that's a great example because we're not going to get positive and negative all the time. So what you have, if you were to graph this blue function right here, you have a vertical asymptote at 4, and on the left and the right side, that graph is doing that. Do the cars meet? No. So the limit does not exist. But what we've done is we've went a little farther into detail on that problem, and we've said, hey, the cars don't meet at 4, The limit doesn't exist, but we've also said what's happening. To the left of 4 and to the right of 4, this graph is going to infinity. Okay? All right. But again, it all started because when we first plugged in our 4, we got this. So it was the third in our notes there, the third of those options. Vertical azimuth. Good one. Rachel, thank you for asking about that. Okay? Even though I'm sure you were the only one who didn't get that one. Everybody else, I think, was fine.
35.
What's that?
35.
35. Okay? So, same picture. X approaches 1. Now, notice it's f of x minus 3. So, we're going to put a 1 in. 1 minus 3 is negative 2. So, what's f of negative 2? 0. Then we put a 1 in here. 1 plus 3 is 4. F of 4, 3.5. So on number 35, we plug in a 1, we get 0 over 3.5, which is?
Just do it again. Oh, 0. Just no. Okay.
Right? 0 on top is fine. Yeah, 0 divided by 3.5 is 0.
Yeah, right.
See, we're outsmarting ourselves, right? We become so intelligent that the simple things are escaping. That's one of the downsides of being so brilliant.
Yeah.
Yeah, I just learned a little. All right. Okay. All right. Appreciate the fact that we didn't laugh out loud. All right. So that's it. That's it on that one. Okay. What else? What else? What else? There's got to be some others. Oops. I guess I don't have the other page. 42. Do I have 42? Oh, it must be on the other page. Okay. Tell me what 42 is.
It says going to sketch.
Oh, okay. Oh, yeah. Yeah, that's a good one. Okay. So, have we done one of these on a quiz before? You don't think you ever want to? Oh, this is an easy one. Sketch the graph of a function that has all of the following properties. Label the axis and indicate units. Okay. So, we look at that. Looks like we got x, and this would be f of x. And what does it say? Number 1, f has domain from -3 to infinity. So what's that tell you? What's that tell you about this graph we're about to draw? Well, okay, yeah, I know it says -3. There might be a vertical asymptote there, but it might not be either. I mean, just based on number 1, I guess what I was looking for, will there be any sketch to the left of -3? There will be nothing on this picture to the left of that. That's really all that we know. And it's going to have sketch to the right from -3 on. And it does not include -3, looks like, right? Has a range of -infinity to 2. So there will be nothing above 2 in this graph. Okay? F of -1 equals 0. What's that tell me? There is a point, right, at -1, 0. I know it tells me everything. But, okay, f of 0 equals 0 is that point, and f of 5 equals 0 is that point. Okay? So I know those points. The limit as x approaches -3 from the right is -infinity. So now I would agree actually with what you said about -3 being a vertical asymptote, and to the right of it, it's going down like so. Right? That's what I know from statement number 4. Statement number 5, as x approaches 2, the limit is -3. What's that tell you? As x approaches 2, the limit is -3.
There's like a point Or at least a whole.
Very good. There's something there where the cars meet. The cars would meet down there. Now, it might be a hole. If you really want to be creative, you'd make that a hole, or you could make it a filled-in point. Doesn't matter. But the cars are going to meet them. So it's got to be a hole or a filled-in spot, and the graph has to come off of there. So maybe it's a minimum. Wouldn't have to be a minimum, right? Then just the cars would have to meet them. Okay? So I'll fill that in when I fill in the rest of it. And so could be filled in or not filled in. So I'll fill in half. You probably shouldn't do that on yours, because I don't know if that means anything. I guess I would assume you filled it in, just aren't very good at color. All right. The next one. As x approaches infinity, the limit is 2. That's a horizontal asymptote at 2. Now, we said that you could, and so I've badly run out of room here, so I'm going to draw this. So here's 2, here's 3, here's 4, here's 5. Okay. This is to scale, as you can see. All right. So f of 5 is 0. So I've got a horizontal asymptote. Now, we've said that a horizontal asymptote could be crossed. So it could go up and then go down and up and down, except for the fact, in this one it could not. Why? Range. That would be outside the range. So this one is going to come up underneath and do that. So there we go. Everything is there. So it says, sketch a graph that has all of these properties. So from here, you can do about anything you want. I could go like that, but I certainly wouldn't have to. And then it's got to cross here. And then this could be a minimum, but it might not. It might go down here farther, whatever, doesn't matter. And then it's going to hit there. And then who knows, maybe it does that, I don't know. It wouldn't have to, but it could, right? But it's got to go through those points. It can't go above 2. It can't go to the left of -3. It's got to go down to negative infinity there. It's got to approach this horizontal asymptote there, and it's got to cross those 3 points. And the cars, and that is not supposed to be a little blank. Okay, and the cars have to meet there. That dot could be the minimum, could have been, but it wouldn't have to be. Okay, could be. This could be an open circle here, would be fine. These have to be dots that it goes through. Okay, that kind of thing. That's not too bad, right? I like that problem because that kind of ties in these different things that we've done, and again, kind of understanding the big picture of that. Okay. Anything else? Okay. Not much else to say on. Probably Newton's Law of Cooling would be good for you to review. I've got one of those on here, so maybe I'll pass out this worksheet. You might want to work on that first and make sure you get on your calculators. You know the formula. You can plug the numbers in where they need to go. You can solve on your calculator. That's really the main thing you would use your calculator for, is a Newton's Law of Cooling to solve one of those. Okay, and then beyond that, it's pretty much no calculator. Matching the slope fields, go back to that worksheet. I don't really have any review for that, so go back to that sheet, those worksheets we had with the matching of the slope fields, and look that over. Okay? All right. So notice on my directions, that's probably what the directions on the test will be too. It says evaluate the following limits. If the limit does not exist, show why. Well, that's basically your infinity. That's your check the left and the right. Or just if it's one of the infinity ones, x is getting bigger, just you say does not exist and infinity, or does not exist negative infinity. So there wouldn't really be anything to show on that, on one of those. You just give that answer. But a vertical asymptote one where you got to check the left and the right, that's kind of what I meant by show why. So essentially just working the way we've been working. Okay? And I tried on the Newton's Law of Cooling, I tried to give you several different ones to do so you can practice all within the same problem. But look at that, it's only 2 problems. Number 1, number 2. Okay.
I was wondering if I could leave 11 to go
you'll help me with that.
Do I have answers to this? Again, I think it would be good to go into the book, that 56 through 80 section. I think doing some more of those would be good practice as well. And remember, you can always type. Did I show you how to type into your calculator? Does everybody know on the limits? Does everybody know how to check those on your calculator? Right? So, oops.
Oh, no, this is the one I have.
Okay, so everybody knows on your calculator to check, like that second one there, B, right? You can just type it right in, and I got that from the next to the 9. Same place you get your derivative stuff, it's right there. So when you're going through the book ones or these worksheet ones, you can check them, pretty easily. And you can put a little plus or a little negative if you need the right and the left part of it. So.